Hang on. So, hello, everybody. First of all, I want to thank the organizers for inviting me. This has been a really good, informative conference, and I think knowing what I know about healthcare today, this is probably the best way for you to learn a lot of information quickly. And I think it's fantastic that you have the researchers and the clinicians here actually explaining it, because if they can't explain it, then no one really can, right? So always ask a lot of questions and get as much information as you can, because I think that's the way to navigate our system now. So I'm on faculty at Hopkins, and I have this really great opportunity to work with the clinicians and researchers there. Is it echoey to you too? Okay. I have this great opportunity to work with some fantastic people, and many of them are very interested in solving this problem of TM or MS or other neurodegenerative diseases. And my focus is a little bit different. So I think that's incredibly important, but I recognize that there are a lot of people who have the disease and have a lot of problems walking and moving. And so my training is really designed to try to implement better rehabilitation. And I'll talk later this morning or later this afternoon about neurorehabilitation specifically. Today, what I want to share with you is some of the results that I have from my research. So feel free to ask questions as I go. I know I talk quickly, and I'm trying to slow down, so definitely let me know if it's too fast. So my title is Relating Sensorimotor Function to MRI. So what I want to do is really try to relate what we know about movement to what we see on the MRI. But I am most interested in really the practical aspects of this. So why does walking go bad in multiple sclerosis? Why do some people have a really hard time walking and others really do not? So we know that walking is a really complicated task. It's actually very easy if you have no problems. But as soon as something goes wrong, it becomes very complicated and very frustrating. And we know that any change in the central nervous system can make walking more difficult. And this can be for many different reasons. Just simply old age makes walking difficult, but also things like transverse myelitis, stroke, or MS. Now, just briefly, what we know about MS that I'm most interested in is that it's really difficult to measure this physical decline, because as you know, everyone looks a little bit different. So everyone, their MRI looks a little bit different, and their movements look a little bit different from one another. And we know that there are white matter changes in the earliest stages of the disease, and white matter changes mean the nerves themselves are, and the myelin surrounding them are impaired. We know that there's degeneration of the axons, and we know that it's really difficult to relate impairments to specifically clinically involved white matter tracts. And this last one I'll explain more in detail, so just stay with me. So my take was we really need more studies to better understand how these impairments, how these functional problems relate to the pathology. And if you think about stroke rehab is 10 years ahead of what we do with MS. And that's really unfortunate, and I don't think it's necessary. So what I'm trying to do is basically take what we know about stroke, better understand it, and apply it to what we do with MS. And I think that we need to at least start there to improve the rehab for people. So as you've learned so far quite a bit in this conference, we know a lot about the pathology of MS and other diseases, right? And we know that function is usually impaired in some way or another, if briefly or for long term. What's missing, there's this big gap, though, in what we know about the pathology. So you can learn all about the genetics, you can learn all about the cellular properties, but what people really want is to improve their function, right? You really want to just live your life and enjoy your life. So somehow we need to bridge this gap. So my idea, and the data that I'll show you today, is to measure impairments. And by impairments, I mean strength and sensation, so kind of going back to some basics. And I'm also going to measure white matter fiber tracts. And I'm going to do this using some specific analyses in MRI. So the goal is to determine to what extent nerve fiber recovery is associated with the recovery of walking and physical impairments of relapsing remitting MS. So in relapsing remitting MS, people have exacerbations where they wake up and they have tingling in their arms or legs, and they have weakness, and this makes it very difficult to walk. And in some people, within a month or two, things improve to the point where they don't even remember having the exacerbation. And in other people, that doesn't happen. And they have impairments that continue and get worse and worse. So what I'd like to understand is what's the difference between those two groups of people? Because we really want everyone to improve from an exacerbation and get back to their baseline or close to their baseline if we can. So why is this important? We need to understand the extent of recovery in everybody. And if we understand that, then we can maximize the recovery. And we do this by designing better, specific rehab programs. Not general, but being very specific. And I think that's the key to dealing with many of these degenerative conditions. And the third one is really important, too, because the measures that I use can actually also be used to test whether drugs work better or not, and in a much more quick fashion, so we can determine in a shorter period of time what medications will work. So what we don't know is, do specific MRI findings determine specific impairments like strength sensation? And how do they contribute to walking? Okay, we know there are common physical symptoms, right? We know that often there's sensory loss, there's weakness, there's something called ataxia, which is just a kind of a complicated word to mean inability to coordinate multiple joints. So you know the doctor always says, okay, touch your nose and then touch my finger. And it seems like a really silly task, but really what they're looking for is how well can you coordinate your arm? Because to move in a really straight way like this is actually very difficult. I have to coordinate my shoulder, my elbow, my wrist, my finger, all at the same time. And if the timing of all those events doesn't happen exactly right, then you end up swerving a little bit, even though you're trying to go straight. We also know people have poor balance, and falling is a big problem. And all of these things combined make for a problem walking. So as Dr. Greenberg explained, I work in a motion analysis laboratory. And it's a big space like this with a lot of technology sort of all around the edges of the room. And the idea is we need the open space because we need people to be able to walk. And we need to quantify how they walk, right? And what their strength and what their sensation is. So we measure strength using this little device here. It's called a dynamometer. And the idea is really I hold it in my hand, and I ask you to move in a specific direction, and I offer resistance. And in this way, I can put a number to how strong a specific muscle is. You do this in the doctor's office, too. He has you sit there, and he says, okay, now lift your knee up, and he pushes against you, and he says, okay, good, and he asks you to do on the other side. So that's great, and your physician is using their experience and a rating scale from 0 to 5. But you can imagine that there's a whole broad spectrum in there that's being missed. And the subtle deficits are really important, I'm arguing. So this device gives us a number. So I can track over a period of time. Every time you come in, I can test you the exact same way, and we can see how strong specific muscles have gotten or how weak they've gotten. I also measure sensation using this little device here. What you do is you touch rod A and you touch rod B and you say which one is vibrating. And I, as the tester, can alter the amplitude of that vibration. It's all done in a really very boring way, so it's kind of a boring test. but it gives me a number, again, to say what your vibration sensation is in the toe and in the finger. Your doctor does this in the clinic too, right? They hit the tuning fork and they touch your big toe and they say, can you feel it? And they do it on the other side. And I always wonder, so what exactly are they doing? Because there's no number. And so what they're doing is, again, they're using their experience, and they're counting in seconds how long it takes before you can feel it, before you stop feeling it. And you can imagine 1 second to me and 1 second to you might be different, right? So everyone agrees that it's not the best method. It's just the method that's been used over years. It's clinically very accessible, and it does give some information, but it's also not very specific. So this gives me a number, then again, I can repeat it every day, every hour if I needed to, and I can see how your vibration sensation may change over years. In the laboratory, to measure walking and balance, what we use, we put markers on different bony landmarks on the body, because your bones aren't going to change over time, right? We might gain and lose weight. We might be able to walk sometimes and not other times, but your bones stay the same. So as long as I pick specific bony landmarks, then I can track that every time you come into the lab. We put these little markers on. They're just done with a double stick tape, and they emit infrared light. And this sensor back here, I have 4 of them in the room, and they track every movement you make. So these kinds of devices are actually used for Hollywood, for movies, to do stunts, that kind of thing. But I ask a biologic question with it. Now we measure balance using this little box down here. This is embedded in the earth below the building, actually. It's a force plate. And the idea is I want to see how much do you move when you stand. Because we all move a little bit. So even if you're trying your hardest to stand still, we're moving just a little bit, and that's okay. But if we move too much, that's when I think we're at more risk to fall, and that's bad, right? So again, this little device here can give me a number to how much you moved when you stood. And I'm going to relate these kinds of things to the MRI. And then what happens, you get all wired up in our lab, and then you walk, and someone here walks behind you to sort of coordinate all your wires. And these sensors over here are watching every move you make. So I'm going to give you a demonstration. So this is actual data. This is truly a person, and they do have a head. I just didn't put it on here. It's basically an animation based on where those marker positions exactly are. And I'm going to show you what it looks like. Oh, maybe not. Oh, there you go. So the idea here. So that's a healthy 30-year-old walking across the laboratory. It looks like everyone else, right? So what I want you to notice is things are smooth. The knees bend and extend, hips move. It looks pretty smooth. Now I'm going to give you an example of a different person. This person is not healthy. This person has ataxia, really significant ataxia. So they have trouble coordinating where their foot gets placed each time. And so that's why it looks so shaky like this. That doesn't look like the person before, right? Yes. Yep, so this is so there's a person walking with you in the laboratory, and then there's a person at the computer, making sure that we collect this data. Now, what I can do, once you've left, is I can actually calculate exactly how each of these markers has moved. So I can tell how much you moved at your hip, how much you moved at your knee and your ankle, and how that related to the other side. And more than that, I can compare this to someone who's age-matched and healthy. So I know generally how we should walk. And we walk in a fairly stereotypical pattern. What happens, though, when you have different diseases is that you end up walking differently. Now, many of you have experienced, you go to the doctor's office and they time you walking 25 feet. And they say, ready, go, and you walk as fast as you can. So that's a way to quantify walking. But it turns out that whether you've had a stroke, you have MS, or you have TM, you may walk the same speed. So that's not subtle enough. It's not sensitive enough to really figure out why you're walking differently. But this kind of tool will give me that. If I can go forward, hold on. There we go. So we know when you go to the doctor's office too, they pull up your MRIs, right? And they say, okay, this is your brain, and here are these little gray spots. You know, that's why we think you're weak. And I was surprised finding out that we don't really know that for a fact. And it turns out many people have plaques in their brain with MS, and they walk just fine. And many people have plaques in their brain, and they walk really badly. So clearly, that's not the answer, right? So the goal here is to relate the symptoms to the MRI as much as we can. So I'm using different kinds of MRI techniques. One is called diffusion tensor imaging, and it gives me really nice pictures like this. So this is an actual person, their MRI. This is a motor pathway called the cortical spinal tract. It's the big motor pathway that goes all the way down your spinal cord, and it helps to innervate all of your muscles. And it goes all the way up to the top of your brain. This person has MS and had a really big lesion actually right there. So this kind of technique allows me to know where the lesion is, and I can quantify how healthy these fibers are. I'm going to tell you that we can quantify changes in the brain over time. So this person came in during an exacerbation. This is his MRI. Again, I'm showing you, this is the left side of the brain and the right side of the brain. This side of the brain here, there was a lesion, and you can see that those fibers look different than that side, don't they? 3 months later, looks about the same, maybe a little bit different. 6 months later, this side is now filled in more. And this person actually recovered walking quite well. So I want to show you that this technique allows me to quantify change, and we know we can quantify this change over time. I'm going to tell you, though, that if each of these little a square or circle is one person, and what I'm showing you is data graphing what we know about the brain, that particular tract that I showed you, the corticospinal tract, against ankle strength. And what you can see, what I really want you to notice is this red line right there. It's pretty flat. Now, if strength and that corticospinal tract were really well related, then you would see a line going you would see a line going this way, going down, not flat. Flat means that really what this shows me is that the brain MRI is not giving us information, good information about strength. And this is over about 70 individuals. Yes? Are the MRIs taken before or after walking? Good question. I didn't explain that, actually. So the MRIs are taken usually the same day that I do it. They can't be done during the movement, because you remember the MRI, you have to really be laying flat, unfortunately. I would love it if you could be walking and I could be getting the MRI. That would be much more ideal. But the reality of the technology right now is that you have to be laying flat, and all of the MRIs are taken within a day or two of when I test them. Good question. Okay, so I explained about the brain. Now I want to go to the spinal cord, because it turns out that the spinal cord has all of these tracts that carry information about muscles and strength and sensation. And it turns out that the spinal cord is much more highly correlated with these measures of impairment. But I'm going to start out telling you that the spinal cord is small, no surprise. But I need to give you the impact of how much smaller it is than your brain. So it's about a little bit bigger than the diameter of my thumb. And this is a true picture of a spinal cord segment. It's about 1.5 centimeters from right to left. That's small. That's your brain. And if you put this is your spinal cord in here, if you put that inside your brain, look how much smaller it is. So it's no wonder that the technology has been very slow in coming to being able to quantify what's going on in the spinal cord. And it makes more sense to me, too, that the spinal cord would actually carry motor information, and if you get a little plaque in your spinal cord, it's going to make a big impact in your strength and sensation, right? Versus if you get a little lesion here in your brain, it might make no difference at all. So here's a picture of a spinal cord, and it's as though you cut me right about here through, and then you sort of turned me over and looked at my spinal cord, okay? So what I'm showing you is that these are where the nerve cell bodies are, and this out here, all this gray part is really the white matter that I was telling you about. And I'm going to show you a cartoon over here. So the tracts that I'm interested in, right here, this blue part carries sensation, and we know that from lots of previous studies. This pink part, there's another one over on this side too, that carries motor information, and we know that's a fact. But again, we didn't know until this point really how it related to the MRI. So you go to your clinic and you go see the doctor, and they say, yep, this is your brain up here and this is your spinal cord, and look, this little area right there is a little lighter, so that's probably why you're having trouble walking. So that's helpful, but not really to you, right? So what we want to do is get a better sense of how your spinal cord is relating to this. So this is looking at that segment, actually in a control, so not that segment, a healthy one, in a person. And what I want you to see is there's this little butterfly pattern, like I showed you in the previous slide. These are different kinds of MRIs. This is the typical kind of MRI you get in a clinic, same with this. And if you look, this is your spinal cord, this little area right here, and it's blown up a lot. I can't really see much there. It just looks like a big gray glob to me. Here, this is another view of your spinal cord. They do different sequences when you go get an MRI. Again, it's pretty unclear what's there. If you look to this far right, this is another kind of MRI technique called magnetization transfer. And if you look here, this is your spinal cord, and now look, you can see dark gray versus light gray, and if you squint a little, and you get used to doing that after a while, you can see kind of a butterfly white pattern, except for right over there is really white, and right over here is really white, but it's different than this other side on the right, isn't it? So what I want you to see is that this person actually has a lesion right in their spinal cord affecting this left side here and this part right here. And this other side over here is healthier.
I thought you said the right side of the spinal cord was where the motor.
I did. Well, so both sides. Let me back up one slide just to. So what this is sensory, this part right here, and the motor part is here and over here on the left. I only colored in one because it was a little time intensive to get that part colored. but to give you the idea of that, we know that the fibers that travel on this side and this side carry motor information. So using a specific new technique, this technique actually, magnetization transfer, has been around a while. Just making it useful in the spinal cord has taken a little bit more time. So I want to show you, this is, again, a spinal cord. You can see that little butterfly, white matter. This here, I know it looks kind of like a funnel, but essentially I use different colors to show you that I can track the sensory tract and the motor tract in the spinal cord. And that way I can tell how healthy those tracts are. These are two different subjects. This subject up here has really clear lesions in the left and the right side, where I said motor information was carried, right? The sensory information would actually be right here, and that looks pretty healthy. And I recognize that I've seen a lot of these, so I can tell you that. You just sort of have to believe me that that's the case for this. Now, this person so clearly had these left and right side lesions. Turns out that their sensation was pretty much like a healthy control, but their strength was much worse than a control's for their age and gender. So this matched up. So strength is impaired, and it also depicts that same thing on the MRI. This person over here has a whole lot of white vest right here. So this is one side for strength, and their sensation as well is impaired. And when I measure their sensation is impaired. So higher numbers for this measure are worse than the controls. Strength is also impaired, and that's what you see here on the MRI. Now I'm showing you this over here is the one on the right is the same thing I'd shown you earlier. So if you compare strength with what we see on the brain, you see kind of a flat line. So they don't relate very well. If you take ankle strength from the spinal cord and relate it to the spinal cord, you see a much stronger correlation. And that makes sense to me biologically, right? Because again, the spinal cord is tightly packed, much smaller, carries motor and sensory information, and just a little plaque in that area can cause a much bigger impact. So what we've learned so far. So it's an ongoing study, just to keep you all informed of that. We know that impairments, meaning strength and sensation, don't relate well to brain MRI findings in people with MS. It's not exactly news. That's been known for a little while. The second one, we know we can quantify changes in a major motor pathway, that corticospinal tract that I told you about, in a brain over time and during an exacerbation. So we can see the change from an exacerbation and after the exacerbation. And number three, we know that these impairments relate more closely to the abnormalities in the spinal cord than they do in the brain. So my plan now, next, is to really try to relate these characteristics to locomotion. And that's what I'll tell you about the next time I come to this conference, or you can read about in papers. But before I finish, I want to just express again, my background is in rehab. So I think it's really important to enjoy your life and to keep things in perspective. And so these are my kids, Eva and Maria. But I think just to see little kids smile and laugh gives you sort of that perspective that you have to learn as much as you can about your body and how to improve it and how to improve your condition. But overall, your quality of life is sort of what all of us have. So always protect that. So the question is, if there are sensory damage and motor damage, does that mean they're in separate areas of the spinal cord? Yes, exactly. That's exactly what it means. We know the anatomy of the spinal cord, and it's very detailed. So we know that sensory information is not carried where the motor pathways are. So if you do have sensory and motor problems, there's probably problems in those two areas of your spinal cord. Now, let me clarify one thing, though. That doesn't necessarily mean there are two plaques. Could be one, because it's a small area, right? So it could be one that kind of goes into both areas. Yes. So is the question, do I measure the information from the trunk and pelvis as well? Yes, I do, and I didn't mention that. So I put the markers in specific areas on the pelvis, this bone right here, and it turns out that's a very important bone for keeping our core strength and posture. So it's really important, actually, that I do look at that. That's true. The trunk, so what I do for trunk, I have markers on the shoulders, so I can determine things like flexion and extension and rotation. Yes? Can you ask me? I can't hear you. Yes, so good question. So how are the stroke patient and the MS patient different? So they're very different in one way. A stroke patient will have a lesion that occurs at one time, and once that lesion is over, things can slowly often recover, but not always. In MS, it's different in that you might have little plaques or lesions that happen 1 year, and then a year or two later, you could have a few more. And sometimes they recover, and sometimes they don't. So the important difference is that a person who has a stroke has one impact, has one lesion, often larger than what you see in an MS patient. But an MS patient has multiple, over time, they can have multiple little lesions that accumulate, and that's more what causes their disability. Yes? How often do we upgrade our MRI machines? Very good question. Fairly often. We use a 3 Tesla MRI, so it's about twice the strength of what a typical clinical MRI is. And the software is upgraded fairly continuously. We keep the sequences, so exactly how we look at the data, exactly the same, because otherwise you'd imagine you can't compare over time, right? But we do keep things updated fairly often. That's right. So the point is, right, the question is there must be around other communities MRIs that are not kept up as much. And I absolutely agree. The kind of MRIs you're seeing here are not the common clinical MRIs. Now, most major medical centers have a 3 Tesla machine, and that's not that unusual anymore. But the general clinical MRIs are about 1.5 Tesla. And the difference in having a 3 Tesla is that the resolution of what you're seeing is twice as good or more. But if you do ask, you can go back and ask your physician where you get your MRIs about this and see what they say. Again, I really suggest really asking questions. This kind of thing is not done in the average medical center, but most major medical centers will have it. Yes? Right, good question. So the question is there any risk or any added risk because people are having MRIs multiple times over even a year? All the evidence says no, that there's really not. So you're not really providing, it's not like an X-ray where you're giving exposure to anything. Essentially in an MRI, you're causing the protons to spin in a different way. So there's nothing invasive in that way that we know about. Given that, I will never test someone who's pregnant, even though there's never been any studies showing that. So as far as I know, there's really nothing, there's no added exposure problem. Yes? That's right. Yeah, good question. And I was hoping that this question would come up. So what I'm showing you is anatomy, right? I'm really showing you that I can now quantify where the damage is. And I have the ability to quantify how this relates to physical impairments. But where do I go from here? So my ultimate goal is to better understand locomotion, so walking. I need to use these tools to figure out how people may fit into different groups. There are some people who walk and look more like this ataxia person that I showed you, and those people I think would be treated differently in a rehab than someone who has purely weakness. But that hasn't been done in rehab at all, really. So that's kind of my next step, is to try to group people based on their impairments and see if we can devise rehab treatments that are specific to those impairments. Does that answer your question? Okay. Mm-hmm.
One more question.
Okay.
I just wanted to know if any of your research is published or available online.
Good. Thank you. So is any of my research available online or published? So yes, much of the MRI data is published. What I showed you here actually isn't published yet, but it's close. So you can be looking, and there should be more papers coming out. Thank you for listening.